Myself, Rahul Nagwe. I will be presenting on the topic of bridge engineering and their classification, components, and loads and their failures. This presentation covers the classification and types and their components of bridges, along with key technical aspects such as economical span, afflux, high flood line, shore depth, and the various loads uh, considered in bridge design according to IRC standards. We will also discuss common causes of bridge failures in India with real case studies to balance the perspective, and we will also highlight the engineering marvels like this picture shows the China Bridge in Jammu and Kashmir, the world largest railway bridge, which reflects India's uh, advancement in structural design, material technology, and resilience under the extreme site conditions. This topic gives the insight in both the challenges and achievements in modern bridge engineering. Next slide. In Introduction to Bridge Engineering. What is bridge? A structure designed to span physical obstacles such as bodies of water or roads, allowing to safe passage for vehicle and pedestrians. Bridges are critical elements in modern transportation networks, helping us cross obstacles like rivers, valleys, and roads. They contribute significantly to economic growth and regional connectivity. Every bridge must be designed with careful attention to structural loads, material durability, environmental forces like floods and earthquakes, and long-term safety. What is the importance of bridges in infrastructure? Bridges play a crucial role in connectivity, facilitating transportation, commerce, and the growth of communities. And scope and objective. This presentation is explore the bridge design principles, essential components, and common failures mechanism to provide a thorough understanding. Next slide. Classification of bridges. There are different types of classification. First is of by position relative to high flood lines, structural systems, by material, by functionality. By position to relative to high flood lines, like deck bridges to roadway above water. Through bridges, roadway passes through superstructure, and semi-through bridges partially above the water. In Based on purpose, we have road bridges, railway bridges, and foot bridges by materials. And there are concrete, steel, and composite bridges. In terms of span, they may be short, medium, or long. Structurally, we can categorize them as a beam bridges, arch bridges, suspension bridges, and cable stay bridges. This classification helps in to decide the most suitable types depending on the site and use. Key components of bridges: the superstructure, substructure, and connection and utility include decks, girders, and trusses that directly support to traffic loads. In substructures, comprises abutments, piers, and foundation transferring loads to the ground. In connections, bearings and expansion joints allow movements to drainage and lightning ensures durability and safety. A bridge is consists of several key components. Supporting the part carries a load, bearings, and allows slight move due to the temperature or load changes. The substructures include piers and abutments that support the superstructures. The foundation transports the entire load safely to the ground. Each component must work together for the bridge to perform reliably over its lifespan. What is concept of economical span in bridge design? First, definition: the span length that minimizes the overall construction and maintenance cost while meeting structural requirements. The economical span of a bridge is the ideal distance between supports where the total cost of the bridge is minimized. If spans are too short, the number of supports increases, rising foundation's cost. If spans uh, spans are increased, then rising the foundation cost. If spans are too long, the heavier beams or cables are needed to increasing the superstructure's cost. Include factors, materials, properties, site conditions, load distribution, and construction technology influence the economical span choices. Benefits of this economical span are optimizing the span, reduces the bending moments, and minimizes the material use to leading to cost-effective bridges. Next slide. Understand the afflux in hydraulic design, like bridges. If definition afflux refers to the rise in upstream water level caused by flow obstructions from bridge piers or abutments. Afflux is the rise in water level upstream of a bridge due to the narrowing of the waterway caused by bridge construction. It can cause flooding and damage if not managed properly. Causes and effects: obstruction increase flow resistance, leading to water level rise and potential flooding upstream. Mitigation methods: designing the streamlined pier shapes, advocate pier shape spacing, and optimizing the floodplain allowance to reduce afflux impacts. High flood level in bridge design. High flood level is the maximum anticipated flood water level estimated using historical data and hydrological models. In design importance, determine the minimum bridge clearance to prevent the submergence and ensure structural safety during floods. This helps to avoid submergence during floods and ensure the safety of the bridge and its users. Challenges and practices. Predicting the high flood level is a complex due to the climate variability. Design incorporates safety margins and real-world case lessons. Soar depth and its significance. Definition: soar is the erosion of soil around bridge foundation caused by swiftly moving water. And its types of soar: first local soar, second contraction soar, and third is a general soar. In local soar, around the piers of the bridge and abutments. In contraction soar, at channel narrowings. In general soar, overall riverbed lowering. Countermeasures: use of riprap, concrete aprons, and protective collars ensure foundation stability by mitigating the soar effects. If the soar depth is underestimated, the foundation can be exposed and failed. To prevent this, deeper foundation, riprap protection, and aprons are used. Accurate prediction of maximum soar depth is critical for safety. Bridges must be designed to carry various types of loads. Loads are acting on bridges. First is dead load, permanent structural weight, and including decks plus girders and fixtures. These are dead loads, like own weight of bridges. Second is live load. Live load is a temporary loads from vehicles, pedestrians, and movable equipment. Live loads are traffic, pedestrians, etc., and other processes including wind load, environmental loads like wind pressure, seismic forces, and temperature-induced stresses affecting the stability. In special loads, impact from collisions, dynamic vibrations, and fatigue effects considered in design. The IRC has set load classes. The scope of IRC standards: Indian Road Congress sets guidelines for loads including vehicular classes and safety factors. Key load classes: standard classes such as Class A and 70 are defined loading dimensions and weights for consistent safety designs. Class A for heavy and military traffics, Class A for regular highways, and Class B for lighter traffic areas. These standards help ensure bridges can safely carry expected traffic. Uh, Dynamic loading and safety. IRC provisions account for impact factors and vibrations to ensure durability and serviceability under the real conditions. in international comparison, while similar to AASHTO and Eurocodes. IRC uniquely adapts to Indian vehicle types and traffic conditions. These standards help ensure bridges can safely carry expected traffic. Loads on bridges and their IRC load specifications. In key load types, dead load, live load, and impact load. Dead load is the self load of structure component. Then live load is the traffic load. Impact load is the dynamic effects from moving loads causing additional traces. In environmental conditions, uh, there are three types of loads: wind load, seismic load, and IRC load classes. In wind load, lateral forces exerted by wind pressure on the structure. In seismic load, forces generated by earthquake tremors affecting the stability. And IRC load classes classified as A for heavy traffic, A for highways, and B for light traffic. Bridge failure in India. We have learned lesson from it. Its primary causes is a poor structural design, use of substandard materials, inadequate maintenance, and exposure to natural disasters like floods, earthquakes, and common failure factors in malpractices, etc., etc. Major case studies found is first is a Morbi Bridge collapse in Gujarat. It is a 140-year-old structure and failed primarily due to the fatigue in its critical suspension complex. The bridge underwent cosmetic renovation, but no structural rehabilitation was carried out. Corroded suspension cables and anchorage were left unreplaced, significantly weakening the load carrying capacity at the time of collapse. The bridge was severely overloaded with more than 300 people on it, well beyond its original design limits. No load testing or safety audit was conducted before reopening the bridge to the public. The failure occurred when the fatigue cables snapped under excessive dynamic loading, leading to the sudden collapse of the midspan. This highlights the technically necessity of proper structural assessment, cable replacements, and load regulations in heritage bridge maintenance. In the second case study, Vivekananda Flyover 2016. In this picture, we show this bridge how to collapse. In Kolkata collapse during construction due to the combination of poor construction practices and technical design flaws. The structure being cast was a segmental RCC box girders supported by temporary staging during mm, concreting of one span. The shuttering and staging system failed as it lacked sufficient lateral bracing and was improperly aligned. The temporary supports were overloaded and not designed to carry the fresh concrete load adequately. Additionally, construction sequencing was mismanaged with multiple spans. The collapse was a result of combined structural instability, lack of safety margins in staging design, and inadequate site supervisions. In conclusion, build a safer and smart bridges. It is important of design for as per ICE code and their regulations. Emphasize the rigorous design practices combined with proactive maintenance to enhance the durability. In hydraulics conditions and load considerations, integrate the flood risk assessment and load predictions for comprehensive safety plannings. In innovation and materials, adopt a smart materials and cutting edge technology to future proof engineering, not the safety. IRC companies. Strict adherence to IRC guidelines ensures the strength, economy, and long-term serviceability. A well-designed bridge not only serves transport needs but also stands the test of time.